This is Indistinguishability Obfuscation from Circular Security for STOC 2021. I'm Romain Gay, and this is a joint work with Rafael Pass. First, let me tell you what is Indistinguishability Obfuscation. It involves an efficient algorithm called an obfuscator that turns any program P into an obfuscated program that has the same input-output behavior. And the security we expect from such a scheme states that for any two program P1 and P2 that implement the same function, that means they have the same input-output behavior, the obfuscation of P1 should be computationally indistinguishable from the obfuscation of P2. Remarkably, this notion has been very powerful and remarkably versatile. If you additionally assume one-way function from I/O, you can get a vast number of amazing applications in the cryptography literature. So naturally, there's been a lot of research interest into building an I/O. I'm not going to go over prior works in detail. I'm just going to say that before our work, existing constructions were either broken, they ended up being broken, or actually some of them survived intense cryptanalytic efforts, but they do not have any provable security guarantee. The only guarantee that we have is that we haven't been able to break them. In that sense, their security is entirely heuristic. Or for some of the latest work, they actually have security reduction from simple to state assumptions. But these assumptions came out at the same time they were used to build I/O. Therefore, they haven't been scrutinized for a very long time. In our work, we build I/O from a new circular assumption that has the advantage of being backed up by a general long-standing design principle. And I'll be more specific about the assumption and the design principle later. First, I want to mention independent works, starting with Brakerski et al. That also provide I/O for all circuits from essentially a similar circular assumption than the one we originally came up with. Then there's a work of Weeks that also build I/O for all circuits from a new assumption that has some kind of circular flavor. Also, there's this groundbreaking work of Jane Lin Sahai that builds I/O from well-founded assumptions. By this, I mean assumptions that were studied way before they were used to build I/O, then that we can trust. In particular, this work has the advantage of not relying on any circular assumption. The advantage of these three works, including ours, is that they inherit from BDGM20 a relative conceptual simplicity and like slightly more direct way to get I/O. Also, these three constructions here are all plausibly post-quantum secure because they all rely on lattice-based assumption. It's not the case of original BDGM20 and JLS21. So I want to emphasize the fact that what is really specific to our work is that this new circular assumption that we provide is backed up, as I said, by a general design principle that we will call a strong circular heuristic. And I'll tell you more about it in a while. I'm specifically adding the adjective strong because there is also a weaker security heuristic that's widely used. And that's not exactly the same. All right, so this is our result. I/O from LWE, which stands for learning with error. It's a standard lattice assumption, plus this strong circular heuristic with respect to standard LWE-based encryption schemes. Now let me tell you more about this circular security. It's a quite old idea that, roughly speaking, says take two public key encryption schemes, a black one and a blue one, that are secure. The assumption is that security is preserved in the presence of an encrypted key cycle, just like so. So an encrypted key cycle is an encryption of the black scheme, of the blue key under the black scheme, and an encryption of the black key under the blue scheme. Right. So for instance, you may be interested in semantic security. And then a natural heuristic would be to say, for any natural schemes, semantic security is preserved in the presence of an encrypted key cycle. I have to say natural schemes because we know there are some particular schemes which are believed to be secure, but they are not circularly secure. But all of these counterexamples that we know of are specifically designed for circular security to fail. They're very contrived and artificial. In fact, it's a fairly widely used assumption to say for all natural schemes, this implication holds. The prime example of this circular heuristic is probably the bootstrapping technique by Gentry. That is the only way to obtain unleveled fully homomorphic encryption. What is unleveled FHE? It's an FHE where you can evaluate arbitrary functions with no a priori bound on the running time of the function. This requires the presence of an encrypted secret key cycle. So for this particular application, semantic security is good enough, but there's no reason to stop at semantic security. You may also be interested into, for example, chosen ciphertext attack security or some sort of leakage resilience security, and so forth. So there is a natural strengthening of the circular heuristic, which we call strong circular heuristic, that says for all natural schemes and all natural security notion, the security is preserved in the presence of an encrypted key cycle. This is the heuristic we are going to use. So now let me rephrase our result a little bit more precisely. We build IO from LWE and the strong circular heuristic with respect to a new security notion that we introduce, which is called shielded randomness leakage, SRL security, which I'll tell you more later. But for now, think of it as a security where the adversary has to guess which message is encrypted, like a semantic security experiment, but with the additional information on the randomness that was used to produce the ciphertext, so-called shielded randomness leakage. And the strong circular heuristic is used with respect to two public key encryption. First, Gentry-Sahai GSW FHE, and second, a packed variant of RegEv encryption. Both of these schemes are famous, and their security rely on LWE. We prove our result in two steps. First, we show that if you assume LWE, then GSW is SRL secure. Second, we show that if you assume LWE, if you assume also that SRL security of GSW is preserved in the presence of a key cycle, then IO exists. Combining these two theorems directly gives our result. Now let me tell you more about this SRL security. Take an FHE encryption scheme, 4 bits. So the message M1 and M2 up to MN are bits. And these encryptions, this is ciphertext, have been computed using the randomness R1 up to Rn. Because it's an FHE, it's possible to homomorphically evaluate any function f. And the result will be an evaluated ciphertext, which is an FHE encryption of f evaluated on m. And when doing this homomorphic evaluation, this will also change the randomness of the evaluated ciphertext. And we additionally assume an extra property, which is called randomness homomorphism for the FHE, which basically says, first, you can compute this R sub f deterministically and efficiently from the original message, the original randomness, and the function f. And second, it's possible, given this evaluated ciphertext and the evaluated randomness, R sub f, to recover f of m, sorry. Okay, so there's actually two ways to recover a message. First is to actually decrypt using the secret key, and the other way is to actually use this evaluated randomness R sub f. The difference is that the secret key works on every ciphertext, whereas this evaluated randomness R sub f is specific to this ciphertext, this evaluated ciphertext. It only works for that ciphertext. All right, so now take any FHE that has this property, and that's, for example, the case of GSW. Now we want to define a security notion with some randomness leakage. What is a randomness leakage? Well, it's going to be a shielded variant of R sub f for some particular functions f. And I want to make two remarks. The first remark is that, well, we need to restrict the class of function f for which we reveal R sub f, or shielded R sub f, because the shielded variant of R sub f, just like R sub f itself, will reveal the value f of m. You can open these evaluated FHE ciphertext with the shielded R sub f. So in particular, if you give shielded R sub f for f equals the identity function, you reveal entirely the message m1 up to mn, and there's no meaningful notion of security. So in fact, we need to restrict the shielded leakage for functions whose outputs can be revealed without causing harm to the security. So for now, we will call it predictable function f. So the output f of m is essentially known beforehand. It's not detrimental for security. I'll be more specific in just a slide by what I mean by predictable f. And the second remark I want to do is saying, well, even if f is a very predictable function, let's say a constant function that outputs 0, no matter what the message is, if you give sufficiently many R sub f, that's going to break the security, at least for the particular scheme that we consider. So you need not just R sub f, but shielded R sub f. Without the shield, it's actually insecure. And with the shield, we will prove it is secure under LWE. All right. So just some notation, instead of writing this concatenation of bit encryption, I will write it like this. And now I will give you the actual definition. So it starts off like in CPA security game between an adversary and a challenger. So the adversary, after getting the public key, chooses a pair of messages, gets back the encryptions of the messages, chosen one of the messages chosen at random. So this, remember, this is actually a concatenation of many encryptions of many bits. And then the most interesting part is the randomness leakage, which is obtained by querying an oracle. So first, when queried, the oracle samples the randomness R star and sends to the adversary an FH encryption of 0 under this randomness R star, upon which the adversary chooses a function f and prediction alpha. If the prediction is correct, which means that f evaluated on the bit string m sub b is equal to alpha. So intuitively, that means the adversary already knows the output of f. Then it's okay to reveal the leakage. So leakage is going to be set as R sub f. So evaluate randomness computed from this randomness here. Shielded, that means plus, R star. If, however, the prediction is incorrect, so f of MB is not equal to alpha, then the leakage is just empty, it's bought, and we say the adversary fails. The security experiment stops. Right. So in the case it doesn't stop, while the adversary can do that many times, and at the end it sends a bit B prime, and we say the adversary win if it guesses the bit B correctly, and if he only made valid queries, that is, the adversary didn't fail. We say a scheme is SRL secure if the probability that an efficient adversary wins is less than 1/2 plus negligible. Theorem 1 says that RWE implies that GSW is SRL secure. And a circular variant of the SRL security is essentially the same, except now we have included a key cycle between the FHE and a public key encryption scheme. The difference is now the prediction alpha is about the output of the function f, not only on when given as input m sub b, but also the secret key of the public key encryption scheme. Apart from that, it's a similar definition. Oops. And the theorem 2 that we prove is saying that assuming LWE, assuming GSW and PAC-FF are circular SRL secure, then IO exists. So we think this SRL security notion that we introduce is natural. And one reason we think so is because it occurs in fairly reasonable scenario. For example, the following. Say you have a database and you send it to Alice. Alice encrypts it. That means, she computes the FHE encryption of the database and put it in the sky, along with some FHE encryption of 0. Then later on, you are asked to provide a proof that your database satisfies some predicate, F. And you can ask Alice to produce a proof. And she will send the SRL, this shielded SRL leakage, shielded randomness leakage, as the proof. And everybody can publicly verify this proof, just like so. Take the huge FHE encryption of the database from the sky, homomorphically evaluate the function f, add the FHE encryption of 0. And what you get is an FHE encryption of this under this randomness by randomness homomorphism of the FHE. And you can open this with the proof. You get f of the database, and you can check that it is actually 1. So if these FHE encryptions are computed properly, then the proof is sound. And the SRL security essentially provides some sort of zero knowledge property. In fact, you can use this mechanism to produce many proofs, many online proofs, which are short. As long as you include in the sky many FHE encryption of 0. So this is just a toy application of actually plain SRL security, doesn't require circular security. That illustrates how SRL shows up in some applications. And so to conclude, what we did was to build IO from LWE and this strong circular heuristic with respect to this new SRL security notion that I've talked about, and two well-known encryption schemes that are secure under LWE. So on the negative side, this SRL circular security is actually qualitatively stronger than just circular security with no SRL. There are some subtle differences, and SRL circular security is more sophisticated and more complex. However, the plus side, this is a notion that we think is natural, and we can actually prove it without the key cycle. So the circular SRL notion is essentially the application of a long-standing general design principle, the strong circular heuristic. So following up our work, there's an attack by Hopkins, Jane, and Lin that's actually very insightful and quite simple. That's you can interpret in two ways. The first way is to say, well, they actually give somewhat artificial scheme for which is secure under which is SRL secure under LWE, but it's not SRL circular secure. It is, well, you can think, yeah, you can say it's artificial in the way it does the homomorphic evaluation. It does it in a way that purposefully correlate the randomness with the underlying plain text, and that is exploited by their attack. So clearly, it's important to be careful in what you actually consider to be a natural scheme. And the second interpretation of their attack is to say, well, actually, it's an attack of a stronger variant of SRL for a very natural scheme, actually for GSW. The stronger variance is defined for FHE schemes that evaluate not only Boolean functions, as we do with Boolean gates, but functions with extra gates, arithmetic gates, which allow to compute mod Q, where Q is the modulus of the scheme. Right? So if it's a more complicated class of function, if you define SRL with that class of function, it's a stronger notion. And in fact, it's broken. This notion is not satisfied for even a natural scheme. So this shows two things, that you have to be very careful how you define natural schemes and how you define natural security notion. Right. So this shows some restriction. But as long as you have natural scheme, natural security definition, then you can use general design principle as we did. All right. Okay, now let me conclude with stating some open problems. So this is how the picture looks like, the state of the art. There's some work, including ours, that are conceptually simple, plausibly post-quantum. And there's JLS that has the advantage of being secure, probably secure from well-founded assumption that doesn't require circular security. So naturally, we want the best of both worlds. First, we would like simpler and more direct I/O construction, even simpler than this works. There's room for improvement. And we may want to have a provably secure scheme with post-quantum security and without circular assumption. That would be great. So that concludes my talk. Thank you for your attention.